like to begin with welcome to you all to the Rocks lecture series, and an especially warm welcome to our speaker today, Kirstine Drumm, who will speak to us about phytoplankton communities as climate indicators. So Kirstine is a marine biologist and a rocks postdoc stationed at Copenhagen University. We are very excited to have her with us today. And without further ado, I now would like to hand the virtual microphone over to you. Go ahead.
Thank you so much. Thank you, Anders. Thank you for a very nice presentation, and thank you to all of you who is joining today. My name is Kirstine, as Anders say, and I work on phytoplankton communities within this rocks communities. I'm currently located at Copenhagen University, but I will be moving to Iceland within a few weeks to do more research here. Okay, just a notification to some of you that might not be somebody is unmuted, I think, but yeah. My presentation today will be mainly on the idea behind this project, but also include some of the preliminary results that we have seen so far. And I've only started in October, so it is very early days still. But the overall idea of this project was to investigate the marine phytoplankton community as indicators of the Anthropocene climate change in Iceland. So the obvious question, or where to start, is why are we looking at this? So if we start with Iceland, and for those who have seen some of these rocks talks before, you have seen this image before. This is the production of algae or phytoplankton in the oceans seen annually. In this case, it's for the photosynthetic activity, but it could also be chlorophyll A, and the image would be very similar. And it's just to say that Iceland up here is located in this very productive area. Yeah, and also Iceland is also located in this unique place where you have the cold water coming from the north and the warm water coming from the south, creating this kind of small bubble. I say small, I know it's a big area, but where you have many different. Kirsten, I think you're not, thank you. So you have this small area where you have very cold waters and very warm waters so you can see all these different climate types coming together in a rather small area. And another great thing, I think I'm just going to get my pointer here. Just a second, this is pointer. Oops, laser pointer. And another great thing about Iceland that I'm going to come back to is the monitoring that that's been going. There's been a lot of monitoring of the ocean surrounding Iceland for many years, but I'll come back to that. But going on to the phytoplankton and why we're looking at phytoplankton communities, and this is just a small example of how a community of algae or phytoplankton could look like. And all of these, each of these are consisting of only one cell. And you can say that they're quite simple, or at least they're simple in the way that they're very dependent on the physical factors surrounding them. And with physical factors, just to make it very basic, wind, currents, oceans, predation, and depending on if their physical factor is met, one of these cells will be able to divide every day and sometimes even faster, or not at all for months. So the idea is if we kind of shift one of these physical factors, like if we increase the sun or the nutrient levels, one phytoplankton community would appear, whereas if we change the salinity and predation, we will see different patterns. And I included volcanoes because we're in Iceland, and it'd be cool if there were some correlations there. But the whole idea is that the communities of algae will change according to what they're subjected to. And to monitor the phytoplankton community, the classic way of doing things is using a microscope. And I know that some of you who are listening here today are not that used to sitting in front of a microscope. So just to let you know, this could be a drop of water where there's this actually water from Iceland. It's a bit old, so there won't be that much diversity here. But you can go up the magnification. This would usually be just a drop where you don't see anything. I don't think I have this playing yet. Yeah. But then you can just see some structures in there. But if you go up, you will see more and more structures the closer you get to it. So things will be lying in the bottom, but also if you go a little bit up with the microscope, you can see that things will be lying in different layers, depending on where in the water column you are, even though it's just a small drop that we're looking at. But you can see different structures here and there. But when you get really close, you will actually start to see moving things. And again, this is a bit of an old sample, so not very much is moving anymore. But you can see small stuff swimming about. These are phytoplanktons, many of them at least. And to the last magnification, this is the highest that we can go on normal microscopes. And suddenly you can see structures that you didn't see before at all, like these beautiful diatoms that we have here. Don't know if you noticed there's a small zooplankton running around up in the top corner, but it kind of requires that you go really close to see all these details. And this is the classic way of monitoring that's been going on for many years. And it requires a lot of knowledge of these different species that we're looking at. Right now, I think we only have like 5 different phytoplankton species in this, but you need to know them, and it takes a lot of time to find them. But a very good thing about using a microscope is that you can count them. So you can actually go and see, okay, this species is very similar to this and this, so it's most likely the same. And in this image, there are 6 or 7 of these. So you will have a number for it. Because a new way that we're trying to include in this project as well is using environmental DNA or eDNA. And basically, the method is that you take a big water sample, you filter it down on a filter, and then all the living organisms in this water sample will be present on this filter. That's the idea, at least. And then you go through a very long process of isolating and taking out all the DNA from this filter. And in the ideal world, you will end up with a long list of all the species that's present within this water sample. So it sounds amazing, and it is an amazing tool to be used, but of course, not everything is perfect. For example, you can't get a number of how many of the different species was there, you just get a long list. And this long list is because this is still a rather new technique that we're using, eDNA. Many of the species won't be named because we actually don't have DNA for them. So that's a big missing factor with working with eDNA that I'm also going to address in one more slide. But combining this classic way of monitoring using microscope and using eDNA, oh yeah, I need to say this as well. Another very cool thing about eDNA is that we have the potential to go back in time. And this is because the DNA is stored, and in the ocean it's stored in the sediment of the oceans. So if we go down into the sediment, we can actually use eDNA and try to reconstruct the community that used to be there back in time. But using microscope and eDNA brings me to my first objective, which is to identify some of these patterns in phytoplankton communities that could be related to the physical factors. And to do this, I have allied myself with very good people at the Marine and Freshwater Research Institute. I'll probably refer to that as HAFRÓ many times. But at this institute, they've been doing all this monitoring that I mentioned just in the beginning. So all of these dots that you have here surrounding Iceland, they're actually stations where the oceans around Iceland are being monitored several times a year. And in particular, in the spring growth that they have, they also monitor phytoplankton communities. All right, not so much communities, but they monitor all the phytoplankton there. With this data, we can try to find some of these patterns. And also they have started to do eDNA filters that we will have a look at as well. So so that's going to be one of my first objectives. And the next objective seems it's so basic. It's vertical transfer, and it's basic in many sense, but it's also very important, because if we are able to identify some of these phytoplankton communities, we still don't know what's actually stored in the sediment. So going from the full community in the upper water column, what will actually sink, how much will be eaten, and how much of the DNA will be left when we actually go to the ocean sediment. So one of the tasks that we're going to do is to follow down the water column to see what species are still in the oceans when we go to the sediment floor. And to do this, again, I have allied myself with HAFRÓ and also GEOS, where they have a lot of knowledge working with eDNA, but also going into the sediment with sedDNA. And because we assume that not all of the species found in the upper surface, we are also looking for what we call proxies, or key species that kind of represent a community. So we're trying to find these as well during this objective. And the last objective is what I call culture collection. And for those who know about culture collections, it might be a little bit taking my mouth full, as we say in Denmark, but because the general idea of a culture collection is that you have a lot of different species and you grow them and you can use them from a lot of things. Basically, what I want to do, I want to have a culture collection for a very short period of time, and then I basically just want to kill them, get their DNA, and identify them. But I still call it culture collection here, just for popular term. But here I want to take all of these species that we do not have don't have these DNA barcodes for. So the eDNA have to correlate to something existing in the system, and we're missing DNA for many species. So the live samples that we're getting from the vertical transfer will also be used. So we isolate them and grow them, and then we obtain the DNA barcode that we can use to enhance the eDNA that we're collecting, together with the phytoplankton monitoring to try to identify proxies, also together with the vertical transfer. And hopefully at some point we can go in and say whether, and hopefully of course, that phytoplankton communities are perfect as climate indicators. So I started this project in October, and I've been working primarily with these objectives. Excuse me. And just to start off light, I'm going to start off with this culture collection. There's also some nice images from this, so yeah, it's a bit of a light mode. To obtain these culture collections, we have the pleasure of having to go out outside and actually catch some of these phytoplankton. And I did this together with Kirstine and Sarah and Nina in November. And what you have here is what we call a plankton net. So you throw that out into the water, you drag it through the water, and you will have most of the water will go through this net that you can see here. So you have a very dense sample of the phytoplankton and zooplankton that's in the water. So a lot of litter would be condensed to that. And from there, you go and sit in front of your microscope. I just want to show this because it is rather basic, and sometimes things can be mystic that are not mystic. But basically, you have this the straw, where this is a mouthpiece, and you have a glass pipette here that is, we call that drawn. It's stretched, so it's very small in the end. And if we go back to this water sample that we had before, you just take the straw under the microscope. For this, my mouse doesn't work here, but I'm trying to catch one cell within here, so you can see the opening of the straw coming down there. And sorry for not being so straight on, but when you're recording it, it's backwards too, so it was a little bit difficult, more than I thought. But basically, that's the one I wanted to get, and then I go out and I can clean it. Yeah, and you just wash it until you have one cell that's clean, and then after some time you will have a culture. We call this a culture. So this started off being just one cell that was happy to grow in the water I added it to, and now I have a culture of this species. And this is most of the species that I've collected so far are diatoms. They're most likely the most easy algae to grow. I will focus more on dinoflagellates when I come up to Iceland. At least that's my idea currently. But for the samples that we brought home from November and or December, this is one of the dominating, or not this particularly, but the centric diatom. So this species is round when you see it from the top, but when you put it on the side, it would just look like a string or something. Another species that was quite dominant in these waters were these pinnate diatoms that just look like striped sticks or something. So they grow to quite dense cultures, and this was, I think this one was the most dominating species. And finally, there was also a lot of these navicula. I just want to add that this is a different magnification, so they're not this big as they look here. To make it a little bit edible, I tried to put these different species in some more funny groups. So these are kind of like the spiky ones. And you can see that this is a cell, and then they have these spines going out from their body. And you can see that from these two as well. These are Catosora species. So what our assumptions are with these spikes is that you get a bigger surface, so you actually can float a little bit better when you have these spikes. And even though these species are quite simple in many sense, I think still it's rather cool that they adapt to their environment. So these species are Arctic, and when there's ice in the water, they will actually use these spines because they can break and damage the cells. So they will adapt by not having spines when they're icy waters. I think, yeah. Sometimes we think of them as too simple, I think. They're nice. And then we have those that form chains. Again, these are, this is one cell that's just connected, or one unit. Yeah, this is one cell. So that will be connected to another cell. I don't know if you can actually see that there's like a string going through them. But it is just like pearls on a string that are just, making these very long, beautiful, beautiful chains. And again, we assume that this is a way to have a bigger surface. So again, you are better at floating in the water. It could also be that you're generally bigger in your size. So when there is predation, you can just add some of the other chain forming organisms. So when you are bigger, depending on what's feeding on you, it's an advantage to be big And some of these actually can adapt, so they will make long chains when there's a small predation there, and they will make smaller chains when there are larger predations, because then they can't really catch them. So yeah, again, they may seem very basic, but they somehow sense their environment. And another thing, for those of you who don't have the opportunity to go into the microscope and enjoy them, this guy here, I just find it so amazing that you can go so close to them and see all these details. So for this species here, you can actually see the chloroplasts, the vacuoles within there, and then this round one in the center that you can actually see in several of the cells is the nuclei. So that's where all the DNA is contained. Yeah, beautiful little guys. Then there are also the surprises when you're living or working with living organisms. And this I came across a few days ago. And my first thought, just to give you an idea, this is kind of 1/2 centimeter. So I don't know if you define that as large or small, but in my mind, that's kind of a big thing, because I can actually see that in the flask where I keep these cultures. And to me, I just thought this was some contamination, but when you go closer in, you can actually see that it's a lot of small cells that are making these paths, or yeah, like ant trails or something that they're just forming. And if you go even closer to the species, again, you can see the nuclei in the center and the chloroplast on the sides. And yeah, sorry for being a bit geeky, but I think this is kind of a fantastic structure that they can actually make these forms. And why they're doing this, I don't think we know. Maybe somebody listening here knows why they're doing this, but I haven't seen this kind of structure before. Yes. For the last part I'm going to be talking about is the phytoplankton monitoring that we also initiated looking at. And again, that's done by HAFRÓ, primarily by Kirstine and Kirstine. And I'm only going to be focusing on the past 10 years. We also have data going back to 91, but for the sake of keeping things a little bit simple and light, I think we're just going to focus on this part. And where do I, yeah. So we're also just focusing on 5 stations, going back to this monitoring system again. So we have these 2 stations down in the south. We have 2 northern stations, and then we have the eastern station over here. And the first, excuse me, the first part that we looked at was, and we were curious about, was, is there a difference between these stations? Because the whole project is based on that we can see different phytoplankton communities surrounding Iceland. So the first thing we did was to pool every time a species was recognized, we put that in one of the major groups. I should have said diatoms here, but it's the same thing. So these are diatoms. These are haptophytes. These are very small phytoplankton species, and then dinoflagellates, the green one. These 3 types are the one that we mainly see within the monitoring that's been done, at least for the years that we're looking at. And the thing that we're of course very happy to see is that the stations are quite different from each other, especially if you look at these 2 southern stations versus the 2 northern stations. There is a major difference. And again, or not again, but the eastern station is kind of like a middle thing, and that's kind of an image that we see for many of the different groups that we look into, that they keep ending up like a middle thing over at the eastern side of Iceland. I felt like I had to say something else with this. All right, but because, for example, this haptophyte differentiates a lot from the different stations. We looked a little bit further into that to see what kind of haptophyte actually was there. So, and again, you can see a difference straight away. This on the x-axis here is the different years. So on some of the stations that are a few years missing, but for most of them, it's all there. And this is the number of cells per liter that's found in these samples. And again, a clear pattern here that you have the southern station that are very different from the northern station. So the blue slide here, that's this beautiful haptophyte called the Emiliania hoxie. Yeah, and I was thinking about talking more about that, but I think we're just going to go to the other species here. That's a Phaeocystis. It makes these small colonies as well. They could also be solitary, but so these are two different species, and they're not. This in itself is not brand new, but it kind of falls in line with what other people have seen so far, that the cold water that we see from the north, they will contain Phaeocystis, whereas the warmer waters don't to the same extent contain Phaeocystis, but more E. hoxie, which is known to prefer warmer waters as opposed to the Phaeocystis. And I forgot my track here. Okay, so even though that we see this kind of clear pattern with the north and the south, there are also like many gaps. So why is Phaeocystis not always dominating in like this in this station here in the southern part? And that's where we begin to look at the other species available. So if we compare, yeah, I just wanted to, yeah. So if we compare, this is the Phaeocystis concentration at this the southern station, also the southern station, but for the diatoms. And here you can actually see the gap that is here. So sometimes it will be the Phaeocystis that is dominating, and other times it will be a dinophyte, and sometimes it will be a ciliate, and sometimes it will be a dinoflagellate. But there will be this overlap, and for this station at least, it seemed that it was either a diatom or the Phaeocystis that seemed to be dominating. So the 17 bloom that you see here, you have, oh, the mouse is a little bit tricky, but you have no Phaeocystis, you have no diatoms within this year where the Phaeocystis dominated the whole thing. And just to end up with the diatoms for all of the station, because that was also one of the places where we saw kind of a clear pattern. Again, you have the two southern stations here and the two northern stations here, and there's like a bit of a blue theme going on up here, and a bit more of a dotted theme, I would say. And all these dotted species are these Thalassiosea, which were the pearls on the string. There are a lot of different species of those guys, but these are some of the species that we see more in the north, whereas we see the more pinnate diatoms up in the south. And again, then we have the eastern that kind of have their own patterns. And so now my task is to try to use all of the physical factors that's also monitored for these stations for the same period at the same time, to try to correlate these with the different species, with the different communities, and see what patterns we find. But just the fact that they are so different, these different stations, and we have some clear patterns, that is a very good sign for this project. And I think with that, I will just say thank you for listening, and thank you for all our collaborators. Yeah, thank you.